So let us welcome in last lecture of MAT-601, that is real analysis 2. So already we have seen definition of Fourier series and some results, basic results on Fourier series in previous lecture. So in this lecture we will see some examples on Fourier series. So let's revise the definition of Fourier series. So if f is a Riemann integrable function in closed interval minus pi to pi, then the Fourier series for f is defined as the series 1 upon 2 a0 plus summation varies from 1 to infinity an cos nx plus bn sin nx in the interval minus pi to pi, that is x less than equal to pi greater than equal to minus pi, where here what is an? So an, that is equal to 1 upon phi integration from minus pi to pi fx cos nx dx, n varies from 0 to infinity, and bn, it is equal to 1 upon pi minus integration minus pi to pi fx sin nx dx, n varies from 0 to infinity. So here the constants an and bn are called Fourier coefficients of f, and fx is written as, so in that case we can write fx as 1 upon 2 a0 plus summation an cos nx plus bn sin nx, n varies from 1 to infinity. So you can note that this symbol in the above definition states that the expansion is not actually equal to fx. So this is for approximation, means fx is approximately equal to this summation. This summation contains infinite terms. So there are two remarks. So first remark, if fx is an odd function, which means that f of minus x equal to minus f of x, then if f is odd, then fx into cos nx is an again odd function, because cos is even function and we know, so odd into even, so it will be again odd function. And fx into sin nx is an even function, because f is odd function, sin is again odd function, so odd function into odd function will be even function. So therefore you get, so using previous results, so you'll get if f is odd function, then an will be 1 upon pi minus pi to pi fx cos nx. So fx cos nx is odd function, and already we have seen this result. So integration from minus pi to pi of odd function dx is 0. And what is bn? So in that case bn will be 1 upon pi minus pi to pi, so fx into sin nx, so odd into odd, that will be even function. And already we have seen this result, that is 1 upon pi minus pi to pi, so u1 dx will be 2 times of this integration, that is 2 upon pi integration from 0 to pi fx sin nx dx. Hence, if f is an odd function, so in that case, what is the Fourier series of f? So Fourier series of fx is nothing but summation bn sin nx, n varies from 1 to infinity. So it contains only bn's. So ans will be 0 in that case, and resulting Fourier series will be just bn series. So second remark, if f is an even function, which means that f of minus x equal to f of x, so then fx cos nx, so f is even, cos is again even, so resulting function will be even function, and fx is f is even, sin is odd, so it is even and it is odd, so resulting function will be odd function. Hence an in that case will be 1 upon pi minus pi to pi, so fx into cos nx, so it is even function, and it will be 2 times 1 upon pi integration from minus pi to pi. So sorry, yeah, what I'm writing here, it is integration from 0 to pi fx cos nx dx, and so fx sin nx will be odd function, resulting function is odd, and therefore this integration will be 0. So if f is even function, then bn's are 0, and the resulting Fourier series is given by, that is half a0 plus summation an cos nx, n varies from 1 to infinity. Yeah. So here x less than equal to pi and greater than equal to minus pi. So next we find Fourier series expansion of some given functions. So first example, find the Fourier series of fx equal to x for x greater than equal to minus pi less than equal to pi. So we have here fx equal to x for x belongs to minus pi to pi. So since we can observe here, f of minus x equal to, so using definition of f, it will be minus x, and again, so minus of x, so x, that is fx, so we are putting value of x, it will be minus fx. So hence f of minus x equal to minus f of x for fx equal to x, and therefore this function is odd function, and hence ans will be 0, and the resulting Fourier series of this function will only contains the bn's, it will be just bn series. So we have bn, so using definition of bn, it will be 1 upon pi minus pi to pi x sine n x dx, and this function x sine n x, so x is odd function, sine is odd function, so resulting function is u1, and therefore it will be 2 times the integration from 0 to pi of x sine n x dx. So using integration by parts, so let us consider x as u and sine n x as v. So using integration by part, so yeah, u as it is, integration of sine n x, that will be minus cos n x upon m, and limits from 0 to pi. So 2 upon pi you can take outside of integration, and plus, so secondly, yeah, integration of sine n x, it will be minus cos n x upon n, and this minus, that is minus of integration will be positive, and again integration of cos n x will be sine n x, and it will be upon n, so it will be n square. So after putting limits, we'll get the value of this integration as minus 2 upon n cos n pi. So again we have the value of cos n pi, since you can write cos n pi is equal to minus 1 raised to n, so you'll get the value of bn as minus 2 upon n minus 1 raised to n. So hence the required Fourier series is, that is x will be equal to, x means f of x, so x will be equal to summation bn sin n x, and varies from 1 to infinity. Let us put value of bn minus 2 upon n minus 1 to n sin n x. So 2 you can take outside of integration, and it will be minus 1 to n plus 1 upon n sin n x. So just write down term wise the summation. For n equal to 1 you will get minus 1 square, it will be positive, and that is sin x. For n equal to 2 you will get minus 1 cube, so minus sin 2x upon 2 plus sin 3x upon 3, and likewise. So this is the required Fourier series of given function. So this is first example. Second example, find the Fourier series of the function fx equal to x square in interval minus pi to pi, and deduce the following from it. So you have to deduce these three identities from the Fourier series of function fx equal to x square. So first you will find the Fourier series of fx equal to x square. So it is clear that the function fx equal to x square, so it satisfies this identity, that is f of minus x, it will be minus x square, it will be x square, and that is nothing but fx. So f of minus x equal to fx, and therefore this function will be even function. So you can write. So therefore you can write. So fx equal to x square is an even function, and therefore bn's will be 0, and just Fourier series will be just bn series. So therefore Fourier series of this function fx equal to x square only contains cosine terms, and therefore this series is called cosine series. So we have an, that is 1 upon pi minus pi to pi x square cos n x dx. Again you are using integration by part. So let us consider x square as u and cos n x as v. So using integration by part, this integration will be 2 upon pi integration from 0 to pi. So here x square is even function, cos nx is even function, e1 into e1, that is e1. So that will imply 2 upon pi integration from 0 to pi x square cos nx dx. So using integration by part, the value of this integral will be, yeah, so that will be 4 upon n square cos n pi. Again, since cos n pi is equal to minus 1 raised to n, so you'll find the value of an, that is 4 upon n square minus 1 raised to n. So also you can find a0. So you have to find a0 separately, because if n equal to 0, this value we cannot define. So for that So here n not equal to 0. If n equal to 0, then it will be a0. So you have to find a0 separately, and from definition of an, so a0 will be 2.5 integration from 0 to pi x square cos 0 x, and that will be 1. So it is just x square dx, and the value of a0 will be 2 pi square upon 3. So hence, using definition of Fourier series, uh, the x square will be half a0 plus summation an cos nx, and varies from 1 to infinity. Or so putting values of a0 and an, so you'll get the Fourier series of x square pi square upon 3 plus 4 times minus cos x plus cos 2x upon 2 square minus cos 3x upon 3 square plus cos 4 upon 4x upon 4 square minus it goes to infinity. So you can call this equation as 1. So next, putting x equal to pi in equation number 1 means you'll get the left hand side, it will be pi square, and which will be equal to pi square upon 3 plus 4 times. So you can write here, yeah, 4 times, it will be minus cos pi, it will be cos pi is minus 1, so minus minus, and that is plus 1. Again 1 plus 1 upon 2 square plus 1 upon 3 square, plus it goes to infinity. So you can transfer this pi square upon 3 to left hand side, and you will get, so resulting, that is pi square upon 6, which is equal to 1 upon 1 square plus 1 upon 2 square plus 1 upon 3 square. It goes to infinity, and you will get the first identity which you have to find. You can call this identity as equation number 2. So next, put x equal to 0 in 1, and you will get 0 equal to pi square upon 3 plus 4 times minus 1 plus 1 upon 2 square minus 1 upon 3 square plus 1 upon 4 square. It goes to infinity. Or you can transfer this pi square upon 3 to left hand side, or again you can transfer this 4 to left hand side, and you can multiply whole equation by minus. So you'll get pi square upon 12 equal to 1 upon 1 square minus 1 upon 2 square plus 1 upon 3 square. It goes to infinity. So that will be your second required identity which you have to obtain, and you can call this equation as equation number 3. So finally adding 2 and 3, so we get that is pi square upon 6 plus pi square upon 12, which is equal to 2 times, that is 1 upon 1 square plus 1 upon 3 square. It goes to infinity. Or after simplification, you will get pi square upon 8, and it is equal to 1 upon 1 square plus 1 upon 3 square plus 1 upon 5 square. It goes to infinity, and that is your required third identity which you have to prove. And this is the solution of this second problem. So here there are yeah, four examples for homework. So you can solve, you can find the Fourier series of these functions at home, and it will be end of this topic, that is Fourier series. That is the last chapter of this course, MAT-601, that is real analysis 2, and that will the end of this course also, that is real analysis 2. So I will stop here.